Hi friends, in this video we are going to discuss about inverse Z transform by residue method. So before we enter into the topic, we should know what is meant by poles. So let's define what is meant by pole. So pole is nothing but it's a kind of singularity. Singularity of a function is nothing but a function is not defined at a point. That point is said to be a singular point. Not defined means at the point the function goes infinity. Such a point is called a singular point. Such a singular point is called a pole. So we define a pole like this. A point z equal to a is said to be a pole of a function f of z if limit z tends to a f of z equal to infinity. So whenever we have this condition, that point z equal to a is said to be a pole of the function. So simply we can tell at what z value the function goes infinity, that z value is called pole of the function. So we can easily understand through an example. So take f of z equal to 1 by z minus 5. So here at what value of z this function goes infinity. So already we know that one formula, anything by 0 is nothing but infinity. So remember this formula. So anything by 0 means infinity. So our idea is to make denominator should be 0. So to get poles of any function, we should take denominator equal to 0. So here denominator is z minus 5. Take that equal to 0. So we can get z equal to 5. Therefore, the substitute is equal to 5 there. So 1 by 5 minus 5, that is 1 by 0 is goes infinity. Therefore, the point z equal to 5 makes the function is infinity. Therefore, z equal to 5 is a pole. And more, z equal to 5 occurs only once. Therefore, this is pole of order 1. That means see here z minus 5, the factor value is 1. Only one times it occurs. Therefore, that is called pole of order 1. So pole of order 1 is also called a simple pole. So take one more example. So easily you can understand the concept of poles. So take f of z equal to 1 by z minus 2, z minus 3 whole square, z minus 4 whole cube. So here, what are the points makes this function is infinity? The points are called poles. So easily you can understand that one here. So take all the values equal to 0 here. Z minus 2 equal to 0 means z equal to 2. Z minus 3 whole square equal to 0 means z equal to 3. Similarly, z minus 4 whole cube means z equal to 4. So here z equal to 2 occurs only once. The factor is having one power. That means that is occurs only once. So z equal to 2 is a simple pole. Simple pole means pole of order 1. And z equal to 3 is another z value makes this function not defined. Therefore, z equal to 3 is also a pole, but this z equal to 3 occurs twice. See the power of the factor z minus 3 whole square. That means z minus 3 occurs twice. So it is called a pole of order 2. Similarly, for next z equal to 4 is also a pole. At the point 4 the function reach infinity. Therefore, this is also a pole of f of z of order 3. polar order group. So like that, you can define pole of your function. Right? Now we move for residues. How to find residue after we get the pole of your function? So here there are two cases. First case, residue of a simple pole. Residue of a simple pole. Suppose your function having a pole of order 1, that is called simple pole. Then how to find residue for such a function? That's the case this one. So take residue of f of z at the pole z equal to a. Here z equal to a is a simple pole. So the formula is limit z tends to a z minus a f of z. So very simple formula. So this is a formula to find residue of a function f of z at simple pole, where a is a pole. Then next case, residue of a pole of order m. So residue of pole of order m is nothing but whenever you have more than one order, we can use this formula. And also this we can use as a general formula also. For order 1 also it will satisfy. So the formula is residue of f of z at z equal to a, where a is a pole of order m. So the formula tells you have to take 1 by m minus 1 factorial limit z tends to a d power m minus 1 divided by dz power m minus 1 into z minus a whole power m into f of z. So this is the formula to find the residue of pole of order m. That means more than 1. So let me see one problem. Then easily you can understand that. Before that, we should know one theorem also. First, let me define that theorem. The theorem tells the value of x of n. X of n is nothing but x inverse of x of z. That is, you should know what is meant by first z transform. Z transform of x of n is nothing but x of z. Our answer in terms of z will come. From this you should take inverse transformation. So x of n equal to z inverse of x of z. So whenever we want z inverse formula, we need x of n. That is our aim. Get x of n. So by a theorem, the x of n value is sum of the residues of x of z into z power n minus 1 at its poles. Okay. For the pole, so any function having some poles. At the poles, what's the residue of the function? Then add all the residues, that gives the value of x of n. So this formula you should know. Now we go for problems. The first problem is find z inverse of 2z by z minus 1 into z plus 1 whole square by residue method. By residue method, we have to find the z inverse of the given function. So here the value of x of z is 2z by z minus 1 into z plus 1 whole square. So x of z is nothing but what is z inverse of one function is given, that function is taken as x of z. That is very simple idea. Now we need the function x of z into z power n minus 1. For this function only you have to find the residue. That is our definition tells. See here. So our definition tells sum of the residues of this function. So we need to create this function. So we know what is f of x of z already. Now just multiply by z power n minus 1 on both sides. So you can get 2z into z power n minus 1 divided by z minus 1 into z plus 1 whole square. Now this is nothing but 2 z power, here z simply z means z power 1. So z power 1 z power n minus 1 is nothing but base common. So just we can add the powers 1 plus n minus 1. Here minus 1 plus 1 get cancelled. So you can get z power n divided by z minus 1 into z plus 1 whole square. So this is your function called x of z into z power n minus 1. For this function only we have to find residues. So for residues, first we need poles. How to get poles? To get poles, equate denominator equal to 0. That is, what's the denominator here? Z minus 1 into z plus 1 whole square equal to 0. This implies we can get z minus 1 equal to 0, z plus 1 whole square equal to 0. Therefore, z equal to 1, z equal to here minus 1 comma minus 1. Z plus 1 occurs 2 times. Z plus 1 whole square means z plus 1 into z plus 1. Therefore, z equal to minus 1 comma minus 1. So we can get 2 times. Therefore, at the 2 points the function goes infinity here. The first point is 1. So this 1 occurs only one time. Therefore, this is called a simple pole. So z equal to 1 is a simple pole. Next point is z equal to minus 1. So this is also a pole. At this point the function goes infinity. Therefore, this is also a pole, but this number repeats twice. So the order of this pole is 2. Pole of order 2. That's it. Now we got poles. Now just move for residue. Now take first residue of the simple pole we can find. So residue of x of z power n minus 1. At simple pole what is the formula? Z equal to a. Suppose generally speaking, at z equal to a means what's the formula? If z tends to a, z minus a into x of z into z power n minus 1. This is the formula for simple pole. Now our pole is 1. Our simple pole is 1 here. So x of z into z power n minus 1. Residue of this function at z equal to 1 equal to limit z tends to 1 z minus 1 into x of z into z power n minus 1. That function you have to write. So that function is nothing but 2 power z 2 into z power n by z minus 1 into z plus 1 whole square. 2 into z power n by z minus 1 into z plus 1 whole square. Now cancel this z minus 1, z minus 1. Now just substitute wherever z by 1. So you can get 2 into 1 power n divided by 1 plus 1 whole square. So this is nothing but 2 1 power n. 1 power anything is 1 only. So this is 1 by 2 square is 4. 1 plus 1 2, 2 square 4. So 2 by 4 is nothing but 1 by 2. So this is our first residue called R1. This is our residue 1. Similarly find residue 2 for next pole. So now residue of the function x of z into z power n minus 1 at the pole z equal to minus 1. So here minus 1 is nothing but it's a pole of order more than 1. Therefore you have to use this formula 1 by m minus 1 factorial limit z tends to minus 1 d power m minus 1 by dz power m minus 1 and z first we can define for a general point z minus a whole power m into x of z power n minus 1 and change here also the general point a. First write the formula, then only you can easily understand. So take at the point a. This is the formula. Now apply our point. So residue of x of z power n minus 1. So our z value is nothing but minus 1. So z equal to minus 1. And here our order is also we can fill. Already we got that. So here a value is minus 1 and m value is 2. Order. M is nothing but order. That minus 1 occurs twice. Therefore substitute the two values here. So 1 by 2 minus 1 means 1 factorial. Limit z tends to minus 1. D power m minus 1. M means 2. So 2 minus 1 is 1. So d by dz into z minus a value is minus 1. So minus to minus plus 1. M value is 2 into x of z into z power n minus 1. That is a function 2z power n by z minus 1 into z plus 1 whole square. Now cancel this z plus 1 whole square. So we can get here 1 by 1 factorial is 1. So just leave that. So limit z tends to minus 1 d by dz and take the 2 also outside into the remaining term is z power n by z minus 1. So now just differentiate the term with respect to z once. So this is of the form u by v. Both numerator and denominator are functions of z. So we have to apply u by v formula. So we know differentiation of u by v. That is nothing but v u dash minus u v dash by v square. So we are also having the same form here. So here v u dash, v is nothing but z minus 1, u is nothing but z power n. So if you differentiate that, n into z power n minus 1 minus, then keep z power n as it is. Differentiation of z minus 1 is 1 by z minus 1 whole square. Now wherever z, substitute by minus 1. So what do we get? Therefore 2 into, now replace wherever z as minus 1. So the first term is minus 1 is minus 2. N minus 1 power n minus 1 minus, here also minus 1 power n into 1 is minus 1 power n only, divide by minus 1 whole square. Minus 1 whole square is minus 2 square, 4. So next step we can cancel this 4 and 2. So we can get that 1 by 2 outside. So into minus 2 n into minus 1 whole power n minus 1 can be written as whole power n into minus 1 power minus 1 minus 1 power n. Now take that minus 1 power n outside. So minus 1 power n divided by 2. The remaining term is minus 2n, and this minus 1 power minus 1 is nothing but 1 by minus 1 minus, here minus 1 power n gone outside. So simply you are having 1 there. Therefore next step the answer is minus 1 power n by 2 into, here minus got plus, so 2n minus 1. So this is the answer for residue 2. So our final answer will be the sum of the two residues. Therefore x of n is nothing but sum of the residues of x of z into z power n minus 1. So we got two residues r1 and r2. Just add these two residues. So first residue we got 1 by 2. Second residue we got minus 1 power n by 2 into 2n minus 1. That's all. Here we can take 1 by 2 outside. If you take 1 by 2 outside, you will get 1 by 2 plus 2n into minus 1 power n minus 1 power n. Or you can leave as it is. Here also you can leave this, no problem. Or you can multiply this minus 1 power n inside, or you can keep outside also, no problem. That is your wish. Or you can write this is 1 by 2 into 1 plus minus 1 power n into 2n minus 1. You can keep as it is. No problem. Both forms are correct. So this is your x of n. X of n is nothing but z inverse of x of z. Z inverse of x of z. X of z is nothing but our question. That is our question, given question. Okay. Therefore, z inverse of the given question is 2z by z minus 1 into z plus 1 whole square. So that is our given function. So this is the z inverse of the given function. So here we can take any one form, no problem, all are correct. So I hope you understood. So in the next video we will discuss some other problems.